Okay, hey guys. My name is Matt Bergman. I work at a small consultancy named Nova Fabrica. I'm here to bring cryptography to you. Yes, you. So, great. This is an AES Crypt sheet, or American Encryption Standard, which was officially adopted in 2001 by NIST for encrypting digital data in North America. Before that, there was DES, Data Encryption Standard. That was invented by IBM in 1970. Now, these are symmetrical keys. And this is not dealing with asymmetrical keys like elliptical curve Diffie-Hellman. And now, by this time, all of you are starting to check out because I am talking about math and stuff you don't know. I'm giving you word salads. And why the hell would I ever want to learn cryptography? No math. I wanted to programming because I just wanted to do programming. Cryptography is a minefield. I know this. It is scary. It does not give you context. It is hard. And this is because the unknown scares us. The complicated scares us. And because we are programmers and we need to build systems that do not fail, or we need to make new ways of making hardware that's going to test our phones in ways we never tried before, failure fucking scares us incredibly. We do not want to mess up. C used to terrify me. Back when I was 16 and I was given my first K&R book by my friend Peter Marcello, I saw parentheses, I saw lens, and I ran away screaming because all I could think about that if I didn't copy it down correctly, this would happen. I would blow up the computer. The whole entire school would blow down and I would somehow create the third ice age. I don't even know how, but it would happen. Just from not having the right semicolons. Sometimes I kind of still feel this way. I admit it. It's sad, but sometimes I think I'm going to do something horribly wrong and your credit cards are going to be stolen on one of the sites I work on. But I press on because I know I am good at this. I know how to test. I know that mistakes do happen and we fix things. These are not the real problems here. We need to face our fears and we need to move forward. Well, okay, maybe the last one, third ice age, I can probably make that happen still. So, look, cryptography is a mess of code and algorithm. It's complicated. It has many namespaces and stuff that doesn't really give you any idea what it's doing. I mean, idea, two fish. What does that even mean? It's a black box. It's black magic. It's a Pandora's box. You don't really want to open it because if you do, you're going to let out all the demons. And all you're going to be left with maybe a little bit of hope, but you probably have already destroyed your system, so nobody's going to care about that. This is a normal response. Completely, I understand. I have it every day when I look at the code I'm working on and this talk and so many other things to deal with cryptography, but we do not have that luxury anymore, people. We do not. Because I think this slide speaks for itself. We are so concerned about privacy right now. We have so many things going on that are problematic. We have seen stuff that we are very unhappy with. I mean, Prism, Bullrun, Muscular, people are hacking into systems we never thought were possible. We need to take this seriously. And it's not somebody else's job to protect us. We need to take that mantle on ourselves. And the NSA is only the biggest worry right now. We have so many other things going on. And so much miscommunication and misunderstanding when it comes to cryptography. There's this thing called kleptography, which means creating secrecy in name only. Creating security in name only. A great example of this is what happened with the British after the Second World War. They would get all their colonies together and give them their Enigma machines. And I'm sure a lot of you know those were broken. So now the British are just watching all the little colonies and all the little secret correspondences and reading them because they're not actually secure, but they thought they were. And this is how we have things like people having SSH keys in their public repos, or encrypting their passwords with DES 333 and then letting them be leaked out. And isn't that great? We now have crossword puzzles for end of time. But we cannot actually have this happen. We need to be smarter. Cryptography is part of our toolkit. We are programmers. We strive to learn, to understand, and to build. We don't just look at HTML, CSS, even when we're back and think, I should know anything about that. Why are we doing that with cryptography? Why are we saying it's too hard? It's not important. Let somebody else decide the standards. Let me just implement this API and this one call and it's all good. We cannot hide from it. Every app we build, everything that's mobile, everything that's desktop, everything that we touch generally has users, generally has passwords, generally has information you need to keep secure, keep safe. Cryptography is part of that. Now, to be clear, cryptography is not all of security. It's simply a part of security. And cryptography is not authentication. It's not reputation, non-reputation, and it's not authorization. It simply helps facilitate these things and create ways to do that securely. Okay, people, I'm sorry. I know I've been droning on. I know I've been saying a lot of words and some of it doesn't make sense. Remember, you guys are awesome. I am awesome, and my hat is damn awesome. So you guys are going to be okay. We're going to get through this, and you're going to learn something. So cryptography at its simplest is about keeping information secret till it's no longer of use to the people trying to get at it. If you take nothing else from my talk, you need to take this. The more vital and important piece of information you're trying to secure, the harder you have to work at making it secure. If you have a session story the last 2 weeks, open SSL standards are probably good enough because after 2 weeks, it no longer matters if they brute force it. But if you're working with very sensitive data that needs to last a long time, you shouldn't be making it digital to begin with, and you should pad it, and you should lock it in a safe, and you should not forget everything else about it because you don't want other people to get at it. You are always the weakest link. Always. There's no hope of that. Security and cryptography can only help so much because eventually people can social engineer around it. We have seen it time and time again. And because I'm talking about social engineering, as part of the Cryptography Association, I'm required to show this slide. I'm sorry, it comes with the territory, people. Moving on. Cryptography is not a superpower. It is a toolkit, I keep saying. It's something you need to learn and grapple with. In fact, cryptography is not even encryption itself. Encryption is simply a part of cryptography, along with one-way hashes, key exchanges, and digital signatures. So, encryption works on 2 principles, and only 2 principles. One is confusion. Confusion is all about removing the link between the encrypted text or the cipher and the plain text. So you got ROT13, Caesar cipher, Adabash. It's just simple letter substitution at its simplest to be understood. The other type is diffusion. And diffusion is seen less on its own, but is exactly as it sounds. It erases the direct correspondence of the cipher and the plain text. Cascadia transposition is a simple way of understanding it where you take a long length of cloth, you write the ciphertext on it, you have a pipe of some diameter, you wrap it around, and the word becomes apparent because of how it's being transposed by the pipe itself. So these two these two principles work together in algorithms to create a way of having an input that has a very much randomized output. That's what's really important when it comes to cryptography. That if you change one letter in a very long sentence, the output is going to be completely different than the other output from that. If you take 2 sentences, they're exactly the same except for one letter, the outputs should be incredibly different. This is what we're trying to do with algorithms. This is called the avalanche effect. It's about using diffuse and confusion in many, many different ways to make it very easy to get very complex and different outputs from the inputs you're putting in. So how does this all work digitally? I'm sorry, folks, to tell you, but it's full of binary, all of it. When you're doing cryptography on a computer, you are not dealing with UTF-8, you're not dealing with ASCII, you're dealing with raw bytes of binary data. You're dealing with them in arrays or singular, but at the end of the day, you are not dealing with words and letters as we know it. And this is partly why you will find when you're dealing with cipher outputs, they're always in base 64 or hex, because it's safer for transporting on the internet because you don't have collision space or anything else. And it is frustrating, especially when you're beginning to try to understand this all, to have a one-word plain text. You're just trying to understand how it's being encrypted. And then you have 3 lines of base 64. I don't know what's going on. It's just something you learn to deal with. So the other big change besides working with binary is the fact that algorithms are no longer kept secret, just the key you're using with the algorithm. This is because you have a private algorithm you came up with yourself that's very secure, that works, but you will never know if it's hacked, and you never actually know if it's actually working very well. Because it could have a very simple backdoor that you're not aware of, and people are hacking you, and you would never know because nobody else is actually testing. This is why algorithms are public, because as many people as possible are trying to crack it, and they're finding that there's no way to do it. So even if you have all the information besides the key, you can't actually get anything out. That's what makes cryptography so useful. It's the fact that with almost all the information, people still cannot get at your data. So a key defines the cipher along with the algorithm. It's basically define a lock. Instead of it being used to fit to a lock, it actually is making the lock itself. It's generated randomly, and it must be kept secret. Your SSH keys are a great example of this, but anything else that you're basically using your computer is not a passcode. It's always some like 128 byte long thing that you would never remember yourself. So this is why like firewalls and other things along with cryptography are considered really important for servers, because if somebody gets to your key, they get access to everything. So algorithms have a key space, or the possible number of keys. This is easily thought about just how secure they are. So if you have a very small key space, you have less security because there's less choices. This is why now we have 128 or 256 or symmetrical keys as default with AES and many others. But even though it's 80 bytes now considered secure. DES was 53 bytes. This is why it's no longer used, because it's not, the key space is so small that it's easy to brute force in less than a couple of months or hours, depending on the system you're using. So I keep saying randomly generated. What does that mean? Prings, or pseudo number generators. I know a lot of you know that computers are magic, that they are not randomized, but sometimes we forget. Sometimes we just think we can use math random in JavaScript. We're going to get wherever we want. Making random numbers is a really difficult concept. It's incredibly hard. I mean, back before computers, we have things called a random number book, where basically you just open up to a page, roll your arm somewhere, point, and copy down the number, check that off, and then open up another page and do it again until you get the number as big as you need it. And make sure you don't go to the middle, because that's what most of people do. That was how you did random numbers before computers. Now we have algorithms at least to try to help you with that, but it's very easy for them to become not actually random. I mean, in Ubuntu, you have two random number generators, urandom and random. And urandom is non-blocking, but also is not actually very random. In cryptography, you actually have a class of random number generators that are important called CS prings, or cryptographically secure random number generators. I know, jargon, but it's important, because if you don't have a good number generator, if they are actually not that randomized, it's so easy to break a key that it becomes useless, and everything else you're doing means nothing. It's one of the most important parts of a cryptography system. I mean, in Taiwan recently, they had smart cards smart cards using 1,048 bytes encryption. I believe it is asymmetrical. Checking out the number random generator and the keys they were producing, out of only 2 million keys, nearly 200 were so weak they were being brute forced by a child in a matter of hours. I know that doesn't sound like a very big number out of 2 million, but it should be astronomically impossible to find even one weak key. And with having so many of them, you would have tens of thousands of people using this card with broken encryption. And that's not acceptable when you're dealing with the safety of your citizens. Even one weak key that's not being guarded against is too much in cryptography. It's about being as safe as possible. So in algorithms, one of the major ways of actually doing all this in the digital world, with actually how they work, is XOR, or exclusive OR. It's a Boolean logic operation. It's really important to cryptography because the output is always affected by both inputs. Exclusive OR. It's only true if one is true. If both are true, it is false. And this means if you take one of the inputs and XOR it with an output, you get the other input. So it's very easy to reverse or to decrypt it after you XOR something. Of course, it's easily broken by itself. By something simple as frequency analysis. So what is actually going on is that we're using them in many different ways, with S-boxing, P-boxing, bit shuffling, to create a much more complex algorithm that using XOR in many different ways. And these are known when you're using a symmetrical key as a block cipher. It's a very simple way of taking bulk data and encrypting it. Block cipher works by taking, you'd have your plain text, You're breaking up into bytes of code, be it 16, 32, 64 bytes, and setting each of those blocks through the algorithm, having the algorithm do its magic, and then outputting as a cipher. Now, block ciphers have many modes, and most can be thought about as additional feature add-ons to an encryption. It doesn't change the central encryption logic, but it gives extra functions that you wouldn't have by just using the algorithm by itself, such as making it no longer blocked by streaming, which means just using one binary bit to a next, or just making it safer, more secure, or adding a MAC so you can add authentication to it. Now, block ciphers have many modes, as I just said. Some of the ones you'll run to most frequently are ECB, or Electric Codebook, and CBC. Now, as I mentioned earlier, Adobe had an issue with DES3 and its passwords and encrypting them with an ECB mode. The reason ECB in particular was such an issue for a lot of people is that ECB mode is not random. This is a photo I ran through AES 128 ECB mode. You can still see it is. Look, it's Finn. Hey, Finn. He's saying algebraic. It's not random. When you put a 16-byte thing through the algorithm that's the same as another 16-byte, it will be the exact same output given a key. So this is why it's very understandable, because these are the same pixels, so they're looking pretty much the same, and you get something that's pretty easy to read. And you can imagine if this was text, it's pretty easy to figure out how to brute force it. So what is the solution? The solution is more randomness. And this is done a lot of the time through an IV, or initialization vector. It adds additional randomness to the cipher output by putting a little bit more in. So the way it works in CBC mode, or cipher block chaining, is that you take the IV and you XOR it with the plain text. Only the first time. The IV is initialization. So the first block is XOR with the IV. It goes through the algorithm, becomes the ciphertext. Then the ciphertext is taken, that block, and XORed with the next block of plain text. It's chaining them together. This is creating a lot more randomness because you're never going to get the same inputs to equal the same outputs this way, because you're adding an extra step. Now, it's not actually random because we don't want true randomness, but it's very close to it, and it's good enough. Okay, guys. I know that was a lot. I know I might have mumbled, and it might have been a little bit hard to hear me at times, but I think I did a decent job. And if not, at least remember, my hat is awesome, Dominic Tat's awesome. He can definitely wear a Doritos bag really, really well. You got to hand it to him. We are doing good. We now can talk about what you really care about, cryptography and JavaScript. All right, so there is much debate right now. One of the classic articles that people are discussing is done by Matasano, and they are basically on the side that cryptography in the browser is impossible. I don't want to debate with you because this is something that takes time and takes a lot of us together to come to any real conclusions. But I do want to give their point of view and at least explain it so that if you want to come to me after the talk, we can have a real chat about the issues we are facing. One, their complaints come to four. The first is the prevalence of content-controlled code, or just the fact that we async out to other libraries. It's not secure because we don't know everything that's coming into the browser, so something might be overriding our cryptography. This goes along with the malleability of JavaScript runtime. It's very easy to change math.random into the same number every single time by just making it a different function. Of course, math.random is not actually the real issue here because JavaScript, I do agree with them, has some major issues with primitives right now. We don't have integers, or at least not 64-bit. We have double precision floating points with like 53 factorial, and I know I didn't promise math, but it's really, really confusing, but basically our integers suck, and we can't actually create prings very easily. And as I said time and time again, without a really great number random generator, you're kind of screwed when it comes to cryptography. And this also goes along with our fact our garbage collection can have issues with not secure erasing, and the fact that some of our functions have timing issues. In a cryptography system, you need to look at every single avenue of attack. And in JavaScript, there's a lot of those. And finally, and the one I will kind of laugh at because we all deal with this daily, older browsers. I don't think this is an actual issue. I do have to say that because we deal with that so often in so many different ways, and we have learned so many ways to get around that I think to worry about the fact that IE8 might not be able to use the JavaScript to encrypt correctly is not the real issue. The real issue to them, honestly, is the fact that they think SSL is good enough. They think a man-in-the-middle attack is what we need to worry about. And that SSL is there. Why do we need cryptography? You already got encryption. I call bullshit. Because SSL is protection from other people on the wire, and cryptography is protection for you on the wire, for you, the user. Why should you always trust me to store your data without reading it? SSL is not going to be good enough always. It protects people, it protects your data from other people. But if I have private information that I really truly care about and don't want anybody to know, having the ability to encrypt it in the browser gives you that option to create that app. If I want to do private diaries or something else, there are not every app is going to need cryptography in the browser, but I do think is a viable and needed thing that we need to think about. So, if any of this interests you, if any of my passion caring about this subject has reached you about that this is something that we cannot ignore as a programmer, as somebody who's part of this community, I highly recommend you read this book. It's by Bruce Schneer. It's Applied Cryptography. It is a seminal work. It is incredibly smart, incisive, and will give you so much information, much more than I ever could hope to give to you in 25 minutes. Also, the Montesano Crypto Challenge, which is told by a lot of people giving these talks, are excellent. They're free. You email them. They send you 8 problems, and then you figure them out. And you send them back and give you 8 more problems that are slightly more difficult. They teach you how to write algorithms. They teach you how they work, and they teach you how to break them. And breaking them is really important because if you don't know how to break an algorithm, you don't know what to look for. So now, hopefully, you do get this joke. If I've done my job correctly, you're going to laugh in a couple of seconds, and now I'm just going to hang my head. Guys, we need to stop being afraid of cryptography. I know it's hard. I know even as much as I've tried to make it as simple as possible, there's so many things I haven't talked about. I haven't talked about hashes. I haven't talked about PGP. I haven't talked about key exchanges. I haven't talked about all the other problems we have right now. I haven't talked about backdoors. I haven't talked about Muscular and what they're doing with Google, which, while not encryption, is social engineering and something we also need to care about. It is a topic of immense breadth, and it's not discussed enough by any one of us. I didn't get into this till about 9 months ago, and that was only because of me seeing that things were being attacked. Beforehand, I wrote my own system for authentication. You know what? I did a pretty damn good job, and I'm still sticking by how my users log in, but I was lucky. There were so many ways I could have messed up. I didn't research cryptography. I didn't know what a nonce was. There were so many ways I could have made things so much worse for my users by not truly trying to dig into something that is important to most of our apps in one way or the other. It's not that scary, people. It isn't. We just think it is. At the end of the day, we can be better. So, I'm Matt Bergman. Please find me after the talk if you want to talk about cryptography or anything else. And if you don't remember anything else besides that, remember, my hat is awesome. Thank you so much.